Welcome viewers. In this video we are going to continue the design of a substation equipment foundation in Eurocode. This is stage 3 out of 7. So what we are going to do in this video is we are going to do the stability check for our previous foundation calculations, which we have seen already the two stages. So first stage is on the screen. You can see that bearing pressure for serviceability limit state and ULS ultimate load combination. Also we are going to check those bearing pressure, and next one is check for overturning and check for sliding. So these three checks, in order to say that our foundation is stable, we are going to do along with the European standard EN 1997. These are the various design stages. We have seen that in series of 1 we have seen that overall overview of calculations. Second one is a foundation and soil parameters, loads and load combinations we have seen already in the last video. And this video we are going to talk about the stability check, and we are do the calculation for that stability check. Fourth one is a foundation board design upcoming, and fifth is design of a bottom slab. Sixth is punching and one-way shear for bottom slab. Finally we are going to conclude with this 7 series with the design of pedestal. So now we move on to our Excel calculation. So you can see that Excel sheet which is showing the bearing and stability check for foundation. So these are the various tables listed here. The first table is mean for the bearing pressure check in SLS load combinations, and second one is bearing pressure check in ULS load combinations. And coming to the next table, so this is for check for overturning in SLS and ULS cases, these two tables. And finally the check for sliding, also we are having two set of load cases. So this SLS load cases are generally to be used for the basic geotechnical requirement, and for these ULS load cases we are going to apply for the member design or the element design. So before going to explain these values inside the table, we need to find the partial resistance factors as per 1997 for spread footing. So for that we need to refer table A5 EN 1997 part 1. So on the screen you can see that this is a table which we need to refer. So here that for bearing and sliding, so what are the factor we are going to consider for the sliding? It is applicable for overturning also. So this is a partial resistance factors for spread foundations. So here that R1, R2, R3 sets are there. So these type of load combinations we need to consider. That R1 is nothing but to design the structure material. So you can see here for spread foundations, the verification of a structural STR and geotechnical limit states set R1, R2, R3 for the following factors, and resistance gamma R shall be applied. So it means for R1 and R3, these are applicable for the structural and foundation sizing, element design, and R2 for geotechnical resistant. So this R2 we need to consider for SLS factor check, and for either R1 or R3 we can consider for ULS load combinations partial resistance factor. So here you can see for overturning and sliding we have considered 1, that is R1 set, and for bearing also we have considered R1 set based upon the code mentioned here. R1, both bearing and sliding it is 1, but for R2 set, that is SLS service load combination, service limit state, we are going to consider 1.4 for bearing and 1.1 for sliding. So it means what are the factors which we are going to arrive from this table? It should not exceed, it should not less than these factors. So that is what this factor is very important. Now we will move on to our table. So in the table now you can look into the detail about the values which is showing here. So this hx, hy, mx, my, vz are the loads from the structure, so which we already seen in the second series. So these are the load values which we have directly linked to the stability table. So this 5 to 4.7, so up to this entire including all the 5 load combinations for SLS we have directly linked here. And this P is a total vertical load. In the second series of video we already calculated this value 82.3 kN, which is excluding the load from structure, which is of soil, overburden soil and the concrete. So this load 82.3 we are adding to this 10.5, that is from the structure load, so we are getting 92.8. So this is applicable for all the load combinations. So like we can just make it this dollar symbol for both the column and row, so that it cannot change. You can just drag this. And coming to the moment at base, so MOY and MOX. So generally this movement MX and MY is nothing but it is act on the top of the plinth level. Say for example, if this is the foundation, we are having this HX used to act in this direction and HY is act in this direction. Both are in horizontal direction, X and Y. So assume like this. And this movement MX, My, which is from the structure, already we are know this, right? So these are movement My and Mx. So this MOY and MOX is nothing but it is a movement at the base of the slab. So total movement. So for that we need to multiply this horizontal forces to the Y bar. Y bar we already calculated in our previous, where it is a capital D plus small d. Capital D is nothing but the depth of foundation from the below ground level, and small d is the pedestal height above ground. So this we already explained in parameter. So you can see this is a Y bar is our consideration now. So this Y bar is 1.8. So we need to multiply this Y bar with the horizontal X in order to find the base moment. So that is what MO0, MOY and MOX is there. So if you link these equations, so you can see this My plus horizontal force X into this I parameter XL, it is 64 is the I64 is the value of Y bar, this one. So we need to multiply this so that the moment at the base of the foundation we can able to find out. So this is for MOX is applicable for MX plus HY into the height. So this is also applicable for all the load cases. We can just track it to this. And coming to the eccentricity is nothing but a moment divided by the vertical force. So that moment at the base divided by the vertical force will give you the actual eccentricity. So again this can be in both the directions. So MOX divided by P equal to EX, actual eccentricity, and MOY divided by P is this EY. So both the actual eccentricity we need to calculate. Now coming to the contact length area. So this contact length area we are already having equations. Suppose this eccentricity is less than the limited eccentricity as we have seen in this parameter. So this is a limiting eccentricity, B divided by 6 and L divided by 6. Already we have considered our foundation pad size as 1.6 by 1.6, so that L by 6 or B by 6 are equal to 0.267 only. So in this case, if you see this eccentricity 0.267 is higher than that, limiting eccentricity is higher than the actual eccentricity, so there is no point of contact length reduction here, so it is mentioned as simply hyphen. So but in this short circuit force load combination case, that is load combination case 15th, if you see it is 0.3, it means it is more than the limiting eccentricity which we have calculated in our previous video, that is 0.267. So it means there is some contact length difference. So how to calculate this contact length difference is, we already explained in the introduction page under this foundation. So this b by x, this x value is defined here as contact length 3 into 0.5 into L minus actual eccentricity. So this calculation is applied here. If this actual eccentricity is less than L by 6 or B by 6 value, that is limiting eccentricity, then this formula is applies 3 into 0.5 into L in minus this eccentricity. So here L means for XY eccentricity, if you are going to consider this EY eccentricity due to movement to Y, then we need to consider the width direction. Similar like for X contact length, we need to consider the length direction if the case that limiting eccentricity is less than the actual eccentricity. So for this contact length in XX is not fine so far, because all the eccentricity are within the limit of eccentricity. So this is what contact length is. In no case there is also some technical specifications from the customer used to mention that contact length should be not greater than 90% or something, it should be mentioned. So that also we need to check it. If it is agree 94% or even 80%, then we no need to worry for this contact length up to this limiting contact length reduction factor. So now coming to the bearing pressure calculation. So this is very big things we need to consider. So first thing is, if actual eccentricity is less than the limiting eccentricity, then these are the calculation procedure. This M1, M2 and M3 are the applicable bearing pressure that we need to consider. So to find the base pressure, we need to understand the criteria as per this listed here. One is, if actual eccentricity is less than the limiting eccentricity, then we need to apply these equations. So whereas M1 plus M2 plus M3 summation of all this will give you the base pressure. In case if actual eccentricity is greater than the limit eccentricity, then we need to find out by using these equations. So these equations you may seen in our first video. This explanation are already provided here. So let we see how it is to be calculated now. So first, in our case, except this one case, last case, all are within the limit of eccentricity. All the eccentricity, actual eccentricity are within the limit. So now let we look how it is calculated. See here first, M1, this equation, how this equation we are going to arrive is, so it is based upon the bending moment equations. We all know that bending moment equation is P by A plus or minus M by Z. So here that Z is a section modulus. Z is equal to BD square by 6. We all know this equation, right? So in order to find out the stress value, that is pressure value, Fy equal to M by Z, right? M by Z means moment divided by BD square by 6. Whereas this 6 we can put it at the top. So it means 6 m divided by bd square. So that is what here we have applied 6 into moment divided by L square by B, and here L square by D. So these equations we have applied here. So this is a simple bending moment equation. So that P by A is nothing but the area. P is a vertical load, total vertical load divided by area. So area we already calculated as a length divided by breadth. So that is what here the equations is calculated here. So this load P divided by, so here that G34 and GI34 are the length and width of the base slab. So these two are 1.6 meter. So it is nothing but vertical load 92.8 divided by 1.6 divided by 1.6 P by area. So all these are same. And coming to this is 6 into MOY. So this moment into 6 into MOY is a moment divided by again this L square B. So this L square means length we have considered as width side we have considered as length, and applying that width here. So by this way we can able to identify this bearing pressure due to this moment MOY. Similar like MOX also need to find. Here it is 0, so no moment, no pressure due to this moment, and summation of all this will have 71.41. So these are the cases. So actually all these cases are applicable for this. Those are having actual eccentricity less than the limiting eccentricity. But in this case, if you see this one direction, this x, y is exceeding the actual limiting eccentricity. So for this alone, we need to go for this kind of equations. So here 2b divided by Lx into b. So this x value we already calculated, that is contact length. So this is a Lx length 1.5 multiplied by b is other directions, and this p 2 into p. So you can see this 2 into p. So by applying this we are getting 77.33 for this case alone. As this case is not applicable because there is no actual eccentricity exceeding the limiting eccentricity in x directions. So that's why it is showing as a value. Now we need to add this M2A plus M3, which is already here, which is 77.3. So we need to add all the things whichever is applicable, then we can able to find out the base here. So this is what the method of calculating this base pressure. The same procedures we are going to follow for ULS also. Only thing, the loads are going to change as per the table value which is to be applicable for ULS load combinations alone. So these values are going to be added here in the, only these values is going to change. Remaining all procedure are same as per the ULS load case. So for this, if you see that bearing pressure is 77.34, which is less than the gross bearing pressure which we have considered as 127 kilopascal. So that applying this divided, actually that gross bearing pressure divided by the actual pressure is having 1.64 in ULS load combinations and 1.52 in SLS load combinations. So all these cases are safe because we are having the factor of bearing pressure as 1 and 1.4 in SLS, ULS and SLS respectively. So this is exceeding, that is more than the partial safety factor. Hence all these are safe, our foundation in bearing pressure. Next, coming to the overturning, into that check for overturning. So let me explain what is that overturning is. So when the foundation assume this is isolated foundations. So this is, if it is going to subject to the moment due to the horizontal force and the direct structural moment, this so this foundation used to twisted or rotated towards the moment. In order to resist this, the self weight of the foundation and the soil weight, overburden soil weight, will create a moment based upon the center of gravity of the foundation. So this will react in opposite direction, so that this foundation will be in stable or equilibrium conditions in order to avoid the rotation due to the actual bending moment happen due to the structural force. So this check we need to do for foundation stability. So how we are going to do is, we are going to find out the total weight of the foundation plus the overburden soil, that is P is the value. So this value we are going to divide it by the center of the effective moment causes, because that bending moment, actual bending moment will cause at the toe side of the base slab. So we are going to take this off distance multiplied with the vertical load P. We can able to find out the resistant moment carrying capacity in both the direction x and y. So this we are going to divide with the actual moment at the base slab, that is this right side moment. So we are going to check whether this is possible to pass in line with the EN 1997 factors. So while applying this, we are getting factors like this 3.09 and 7.35, which are all more than the expected as per the 1997 EN code. So this is states 1 and 1.1 for overturning and sliding. So that is what we can able to say this foundation is safe in overturning. So now let we look how it is calculated. So these are the moment we already calculated from the same moment which we already calculated in the bearing pressure. Like you can see that 24, 10.1, 22. So these values we can directly consider here for the all the load cases. And the restoring moment, that is resistant moment, is a vertical load P into. So here you can see that G34 is size of the base slab, that is 1.6 we have considered in our second series part. So this we are going to multiply with that and we are getting the restoring moment, and in other directions we are going to multiply the width directions divided by 2. So this will give you the resisting moment. If the resisting moment is less than the actual moment, then it is a fail or unstable. So that is a main check. So the same check we have applied for both SLS cases and ULS cases. So this is a table explaining that. So these are all about the ULS load combinations. And coming to the sliding, so as this foundation also subject to horizontal forces here and in both the plane area, the foundation, if the friction between the concrete and the below soil is not good enough to hold the sliding, then the foundation will move these directions and force here. So how generally this resistant force will act means, so due to this weight we already calculate the angle of internal frictions and the coefficient to resist the sliding between the concrete and the soil. So we have calculated here, you can see that this line, so it is 0.29 is our factor. So this factor we directly going to apply in our total weight, that is P. P is concrete, soil and the load from the vertical load from the structures. So we are going to add this 92.8 we are coming, which is coming for this case. So this we are going to multiply with the 5 values, that is 0.29 which we have seen here. So applying this, it is coming 26.92. Then we are going to divide this 26.92 by this actual forces. For y direction, as it is 0, this factor is not applicable, there is no sliding effect for this load case number 11. And coming to the load case number 14, where it is having both side horizontal forces. So both are checked with this phi into P sliding resistance forces. So we are getting 13.52 and 12 respectively. So these are greater than the value defined in EN 1997. So hence we can say this foundation is safe in sliding also. To check for stability criteria, so bearing pressure calculation, overturning and sliding. So with this stage 3 is get completed. We will look more in upcoming videos. Thank you. Look description for more related videos. Subscribe to this channel for more updates. Thank you.